Alrighty, gang, there we are. Welcome back. Today is our sort of last day before exam 2. And the intent today is to give you a little bit more practice with inequalities, rational inequalities. So I want to kind of remind you or lay out the procedure for graphing those things. I'm sorry, not graphing those things, for solving those things, and help you see the connection to the graph. So that's it. We're just going to work a bunch of problems today. Get these things out of the way. We have the book here, the nice collection of problems to choose from. And we'll get to it. All right, there we go. Here we go. I do see a question there in the chat that I'd like to address. No, this time you do not need to reach out to me. If you're going to take the test on campus, that's fine. You don't have to do anything special. Because of the way the testing center is running, I don't know if you remember, we had to like change things around a little bit last time. Because the testing center is so understaffed, they're not willing to let me like send you guys as a class there. But what I can do is make an all-day reservation, right? So if I'm going to make an all-day walk-in reservation, and anybody who wants to take the test at the testing center on campus rather than online with me here, you just show up there anytime in the day and take the test. Now the test isn't going to open until 11 a.m. So that's the one catch, right? Can't do it early. But if you want to take the test at 11 or 12 or 1 or 2 or 3 p.m., any of those is fine. The testing center staff will get you around the proctoring. So they have their own bypass pin. So I'll be setting it up like normal and making a walk-in reservation for you guys at the center. And then if they are busy, the only catch is if you go there at 11, you want to take it at 11. If they are busy, they might say, you got to wait. We got to wait till we have somebody available to proctor you or till we have a computer open. So just be aware of that. But no, you do not need to reach out to me if you want to take the test on campus. You can just show up there instead. Okay, so here we go. Let's do the thing. This is MAC 1140. The section number is 008, which means this is pre-calc. And today is the 21st of October, 2021. It is my wife's birthday. And today, we're going to do more polynomial and rational inequalities. So you did have a quiz due today, I believe. Let me really quickly before we dive into all that, just make sure we're all clear on where we are homework-wise and stuff. So yeah, quiz 3 and homework 4 were both due today at the start of class. If you need more time with any of that stuff, as always, just submit an extension request. Any requests that come in from your class now, I will just be pushing those to the day of the test. There is also this homework, right? Homework 15, which is open now and is due on the day of the test. I popped this open on Tuesday, and I am going to open up one more quiz for you guys that involves the 3.6 and 3.7 stuff that is not on quiz 3. So the intent there is for these quizzes and homeworks to be the main tool to help you prepare for the test. Just make sure you're staying on top of that stuff. All right. So more polynomial and rational inequalities. At the end of class on Tuesday, we talked a little bit about why rational inequalities are a little bit different from linear inequalities and how we can't sort of just do the naive thing and try to solve for x using algebra. And we talked a little bit about what we do instead. Let me just remind you what that procedure is. So your first step is to pull everything to one side. which makes the other side 0. Then, if you have rational functions, if it's just a polynomial inequality, you don't need to worry about this next step. But if you have a rational inequality, you need to have a common denominator. And then combine like terms. So after step 2, you should have everything on one side and all of your like terms together. And if it's a fraction, if there are rational functions, it should be a single fraction with all the like terms combined. After that, you're going to factor everything. Again, if this is a polynomial inequality, there is no bottom to factor. But if it's a rational inequality, then there will be a top and a bottom, and you need to factor both of those things. And also at this step, you're going to write down the numbers that come from those factors. Now, your textbook gives these things a name. Call them cut points, where any of those factors are 0. So you're going to write down the roots of the top and the roots of the bottom. In other words, what we're doing here is we're hunting for x-intercepts and vertical asymptotes. And I'm going to add here that you should note their multiplicity. Right, just like when we're graphing a rational function, we want the multiplicity of the x-intercepts and the multiplicity of the vertical asymptotes. Same thing is true here. When we're trying to solve an inequality involving those functions, we want to make sure we know the multiplicity of those x-intercepts and vertical asymptotes, the thing your book calls cut points. Your next step is to make a number line. You're going to plot those cut points on a number line. And then you're going to determine this would splitting the line into regions, right? That's what that does. Sorry. And then you're going to determine the sign in each region. And that lets you write down the answer. So this is the procedure for solving any polynomial or rational inequality. You pull everything to one side, put all the shit together, factor everything, figure out where that apparatus can change sign. Those are the cut points, the places where the top is bottom or the bottom is bottom. Plot those cut points on a number line, which will split your number line up into some regions, and then you need to determine the sign in each of those regions. It's really this step, determining the sign in each region, where you're finding the solution. And there's a bunch of ways to determine the signs. We actually did this at the beginning of the semester in section 1.8, and to determine the sign in each region there, you were using test points. And it is possible that for some of these problems, you may still want to test a point, but you should never have to test more than one point, because we know this stuff about multiplicities of factors now, and this is a huge time saver. The multiplicity information is important when we're graphing polynomials. It's important when we're graphing rational functions. It's important when we're solving these inequalities. There's like 3 sections on this test where knowing these facts about multiplicities is crucial. So please don't eschew this stuff. Make sure you really are learning it. Practice these things. Let's do some practice together. We'll start with a nice polynomial inequality. Yeah, let's do this one. Move this shit out of the way. So for our first example, I want to solve the inequality 2x cubed plus x squared plus 6 is greater than or equal to 13x. I'm going to do it by following these steps. So my very first step is going to be to pull everything to one side. So I'm going to subtract the 13x over. That'll give me 2x cubed plus x squared minus 13x plus 6 is greater than or equal to 0. So I've pulled everything to one side. That's step one. There is no need for a common denominator here because there are no denominators. And the like terms are already combined. So steps 1 and 2 are done. Step 3 is to factor everything and find those cut points. So now I need to factor this polynomial. How would I factor such a polynomial? It's big, it's degree 3. What should I do?
Rational roots theorem.
Very good. I use my rational roots theorem. So I'm going to come up with those p's and q's. Remember, p's are divisors of 6, the constant term, and q's are divisors of 2, the lead coefficient. So the divisors of 6 are 6, 3, 2, and 1. And 2 is prime. The divisors of 2 are just 2 and 1. So my possible rational roots, those are plus minus 6, plus minus 3, plus minus 2, plus minus 1. That's everything over the 1. And then I look at everything over the 2. Now 6 over 2 is 3. That's already on my list, so I'm not going to write it again. 3 over 2, that's new, so I have plus minus 3 halves. 2 over 2 is 1. That's already on my list. 1 over 2 is new, though. So this is my full list of possible rational roots for that polynomial. And now I start checking using synthetic division. For the sake of time, right, rather than me running through all of these, I'm going to go ahead and start with one that I know works. So I'm going to test x equals 2. And I'll do that synthetic division. So I write down the suspected root and then the coefficients of the polynomial, which are 2, 1, negative 13, and 6. Bring down the 2. 2 times 2 is 4. 4 plus 1 is 5. 2 times 5 is 10. Negative 13 plus 10 is negative 3 times 2 is negative 6 plus 6 is 0. So because the remainder is 0, I have found a factor. So let me come back over here. This is going to be x minus 2 times 2x squared plus 5x minus 3. And that's still greater than or equal to 0. But I'm not done yet. I need to factor this guy. So if I'm going to factor 2x squared plus 5x minus 3, I'm going to do that with the AC method. A times c, that's 2 times negative 3 is negative 6. So I need two numbers that multiply to negative 6 and add up to positive 5. Those are positive 6 and negative 1. So I write this as 2x squared plus 6x minus x minus 3 and factor by grouping. That's 2x times x plus 3 minus 1 times x plus 3. So that's 2x minus 1 times x plus 3. So now I have finished factoring. I have x minus 2 times 2x minus 1 times x plus 3 is greater than or equal to 0. It's true that yes, because the degree is 3, sorry, this came in at the end. It's true that because the degree is 3, we expect 3 roots. It's possible that, like when you get here, that this quadratic doesn't have any real roots. And if you don't have any real roots, I should be clear about this. Record the couplings. Any so the roots that we're interested in for the purposes of solving the inequalities. Factors of 0. These should be real numbers. So I'll put it here. So for the purposes of solving the inequalities, we're not interested in complex roots. I wouldn't give you a problem like that, but just to be clear, because that was a good question that came in the chat there. Yeah, degree 3, I expect 3 roots. It's possible that 1 is real and 2 are complex, non-real complex numbers. But when we're working on these inequalities, they will be real. We're not interested in solving inequalities in the complex plane. That's a little bit beyond the scope of this class. But now we have finished step 3. We have factored everything. What are my cut points? What are the numbers that make these factors 0?
2, -3, and 1/2.
Very good. So I'll plot those on the number line. -3 is furthest to the left, then +1/2, and then 2. And this splits my number line up into 4 regions. And in each of those regions, this polynomial is either positive or negative. I'm looking for the places where this polynomial is greater than or equal to 0. So places where this thing is positive are what I'm seeking. We are now to the step where we actually solve the thing, where we determine the sign in each region. And it's true that you could plug in some test points from each of these regions, but that is way too much work. So I'm going to do this without plugging in any test points. The trick is going to be thinking about the end behavior and the multiplicities. So let's record the multiplicity of each of these cut points. What is the multiplicity here at -3?
1.
1. Good, right? Because the power of this factor is in multiplicity 1 factor. In fact, they're all 1. So what can I deduce from that?
It's odd, so it will change sign.
Very good. Because each of these are an odd multiplicity, we will change sign as we jump over each one. So if this is positive, it would go plus, minus, plus, minus. If this is negative, it's going to go minus, plus, minus, plus. So as soon as I know one of these regions, any one of these regions, I can fill in the sign for the rest of them. I claim that it's pretty easy to get the sign over here. And the trick is to use end behavior. What is the end behavior for this polynomial?
Down to the left and up to the right.
Very good. So if I'm looking very, very far to the left, is this function going to be positive or negative?
Negative.
Negative, good. So the end behavior here is as x goes to -infinity, y goes to -infinity, and as x goes to +infinity, y goes to +infinity. In particular, as x goes far off to the left, y goes down, which means we are negative in this region. And the second piece here actually tells me that we're positive in this region. So I can get those 2 signs just from the end behavior. And then I can fill in the rest of these using multiplicity. So as I jump over this guy, I'm going to go from negative to positive because he's odd multiplicity. And as I jump over this guy, I'm going to go from positive to negative because he's odd multiplicity. And then we can kind of check that this is correct, right? We knew this from end behavior, but also now that I know this is negative and this is multiplicity 1, we should change back to positive, and we do. So that's it. Without ever testing a point, without ever plugging a number in, I have solved this inequality. What is the solution set? Yeah, so the end behavior here comes from this term. It's because the lead coefficient is positive and the degree is odd. All right, so my inequality is equivalent to this inequality. This inequality I can solve from this sign chart, this number line. What is my solution set? Where is this thing greater than or equal to 0? Let's just start with the endpoints of the intervals I'm going to use. Is this region a part of my solution?
No.
No, right? Because this polynomial is negative in this region. I'm looking for places where this polynomial is greater than or equal to 0. Is this a part of my solution?
Yes.
Yeah. So from -3 to +1/2, we'll worry about brackets or parentheses in just a second, union with, this is not a part of my solution because that polynomial is negative there. This is a part of my solution because my polynomial is positive there. So the other interval here is 2 to infinity. And the infinity symbol always gets a parentheses. What about the 2, the 1/2, and the -3? Should I put a bracket on this 2 or a parentheses on this 2?
You should put a bracket. Wouldn't it be for all of them?
Yes, very good. So if I plug 2 into this equation or this inequality, this factor is going to be 0, which makes the whole left-hand side 0. And 0 is greater than or equal to 0. So this is going to get a bracket. And for the exact same reason, these guys also get brackets. If you plug in 1/2, this factor is 0, which makes this whole thing 0. And 0 is greater than or equal to 0. When you plug in -3, this is 0, which makes all this 0, and 0 is greater than or equal to 0. So here's my solution set. If this was a strictly greater than, rather than greater than or equal to, these would all be parentheses. So kind of the very last thing you need to do is check and see whether your endpoints are a part of the solution set or not. And for a polynomial inequality, that's pretty easy. If it's a greater than or equal to or less than or equal to, you'll include all the endpoints. For a rational inequality, you need to be careful because maybe one of these endpoints would make the downstairs equal 0, and then you would have to exclude those. But we'll look at something like that in just a minute. Are there any questions about how we arrive at this solution? Okay, just for fun, let's look at the graph. The graph of the polynomial p of x equals x minus 2, 2x minus 1 times x plus 3. I've got a root here at -3. I've got a root at +1/2. And I've got a root at +2. My end behavior I know is down on the left and up on the right, which means I have to cross like this here, and like this here. So the graph of this function is something like this. This is -3, 2. And remember, we said we're looking for places where this polynomial is greater than or equal to 0. Well, that would be where is the graph above the x-axis? It's above the x-axis from here to here, which is -3 to +1/2. And it's above the x-axis everywhere to the right of 2, which we see here. So yeah, this is consistent with what we've seen already, right? This piece would be a part of my solution set in these x values, and this piece so it's exactly what we thought, from -3 to 1/2 and from 2 to infinity. Okay, let's do this for something a little more complicated. First, any questions at all on what we've done here? Okay, let's try something a little tougher. Let's solve the inequality 1 minus 2x over x squared minus 2x minus 3 is greater than or equal to 1. All right, what would be my first step?
Pull everything to one side.
Yep, I need to
So
pull.
would you subtract the 1?
Yes, sir, that's exactly it. You could also, if you wanted to, subtract this whole chunk over here, but I would much rather subtract a 1. So that'll give me 1 minus 2x over x squared minus 2x minus 3 minus 1 is greater than or equal to 0. Okay, so that's step 1. What now?
Needs a common denominator now.
Good. So my goal is to write this all as one big fraction with everything factored top and bottom. In order to get there, I need to have a common denominator between these two pieces. So 1 minus 2x over x squared minus 2x minus 3 stays what it is. And then this 1, I multiply up and down by this denominator to give it the same denominator. So it's going to be minus x squared minus 2x minus 3 over x squared minus 2x minus 3. And this is all still greater than or equal to 0. I need to remember that the tops and bottoms of fractions are always in parentheses, right? Specifically, this top is in parentheses. So when we subtract, that minus sign is going to need to be distributed. This is 1 minus 2x minus parentheses x squared minus 2x minus 3 all over that x squared minus 2x minus 3, and all still greater than or equal to 0. Yeah, good question. So should you factor the denominator before or after finding the common denominator? I would wait, because if you imagine at this step, I factor the denominator. That's not bad, right? It's x minus 3 times x plus 1. Then I would multiply this by x minus 3 times x plus 1 over x minus 3 times x plus 1. But then I would need to FOIL that out in order to combine like terms. So I recommend doing the common denominator, then factor. So right at this step, if this was already factored, then I would need to FOIL it back out in order to combine the like terms here, the 2x and the constant. So this is 1 minus 2x minus x squared plus 2x plus 3 when we distribute over x squared minus 2x minus 3 is greater than or equal to 0. And then combining all the like terms, I've got a 1 plus 3 is 4. I've got a minus 2x and a plus 2x, those go. And I've got a minus x squared. And then downstairs here, still x squared minus 2x minus 3. And it's at this step that I would suggest factoring. So how does 4 minus x squared factor? Let's see, there's another question in chat there. Would we subtract the common denominator if we didn't have the minus 1? No, the whole reason this piece is here is because I'm trying to have a common denominator between these two pieces. If this piece wasn't here, then we would just jump straight to factoring. So remember, our goal is to get everything into one big fraction on the left-hand side. And that's the only reason we had to do the common denominator step. So without that need, we wouldn't have to do the common denominator step. All right, can anybody help me factor in 4 minus x squared? This is actually a really nice thing.
Difference of perfect squares.
Very good. This is the difference of squares. Remember, a squared minus b squared always factors as a minus b times a plus b. Even if they're not perfect squares, if this was a 3, 3 minus x squared would be root 3 minus x times root 3 plus x. We can always do that. But here we're even luckier. So that top is 2 minus x times 2 plus x, because it is a difference of squares. And that denominator is x minus 3 times x plus 1. So now we have everything on one side. We have a common denominator. All our like terms have been combined, and we've factored. So we're ready to write down the cut points. Plot them on a number line. What do we have for cut points?
2, -2, 3, and -1.
Very good, very good. -2 from this, -1 from this, +2 from this, +3 from this. So -2, -1, +2, and +3. So here's my number line, chopped up into regions by those cut points. And again, my goal is to determine the sign in each of these regions. X-intercepts come from the numerator. Vertical asymptotes come from the denominator. And a function like this is capable of changing sign not only at the x-intercepts, but also as you jump over a vertical asymptote. Think about 1 over x. 1 over x doesn't have any x-intercepts, but it goes from negative to positive as you jump over its vertical asymptote. So cut points are not just x-intercepts. They are x-intercepts or vertical asymptotes. Okay, so we need to determine the sign in one of these regions. That way we can use our multiplicity trick to figure out the sign in all the rest. And these are all, again, multiplicity 1 factors. So we will change sign as we jump over each of those things. So we're going to have that alternating sign pattern. But in order to fill that out, I need to know whether we're starting off positive or negative. If this is a plus here, then this will go plus, minus, plus, minus, plus. And if this is a minus over here, this will go minus, plus, minus, plus, minus. But I need to know. I think the best place to see it is from here.
Wouldn't it be either both going up in the same direction, and both going down in the same direction?
If this were just the numerator or just the denominator, then yes. But the end behavior here is not that of a polynomial, right? This is a rational function. So it's a little more complicated. What is the analogous concept to end behavior for a rational function?
It starts negative and finishes positive.
I'm not sure I understand quite what you're saying. So really quick, I'm going to ask you to focus on that question I just asked. What is the analogous concept of end behavior for a rational function? When we talk about what rational functions do for very, very large x values, what sort of feature on the graph are we discussing?
If as x goes to negative or positive infinity, where it's going to be standing in the graph.
Yeah. So what of all of the graph features for rational functions we talk about, like x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, which one of those things deals with x going to negative infinity or x going to positive infinity?
Multiplicity?
Not multiplicity.
Oh, the lead coefficient being positive or negative.
I think we're thinking a little too much about polynomials. So horizontal asymptotes, right? The horizontal asymptote is the end behavior for a rational function. Because that's right. So think about the graph of a rational function. Pick your favorite rational function. So end behavior is what happens as you go really far to the left or really far to the right. Yeah, that's what end behavior means, whether you're talking about polynomials, rational functions, or anything else. The concept of end behavior for a rational function is its horizontal asymptote. So if I want to know what does this function look like as x goes very, very far to the left, these don't usually go up or down, right? If there's a horizontal asymptote, then it's getting close to that. So the end behavior thing that we're going to use down here to figure out the sign here is the horizontal asymptote. So for this rational function, and I think, again, it's easiest to see from here, what is the horizontal asymptote?
0.
Well, what's the degree of the top?
It would be 1.
So 4 minus x squared, that's a quadratic function, right? There's an x squared there. So the degree of the top here is 2, and the degree of the bottom is also
Wouldn't it be -1?
very good. Yeah, the horizontal asymptote is -1. So the degree of the top is the same as the degree of the bottom. So we're going to take the ratio of lead coefficients. The lead coefficient downstairs is 1. The lead coefficient upstairs, that's the number attached to the largest power of x, is -1. So the horizontal asymptote here is the line y equals -1/1, which is just -1. So if you're looking at the graph of this function, as you run really, really far off to the left, the y values on this graph, the outputs from this function, are getting very, very close to -1. In particular, they must be negative. So on the outermost regions here, your sign will be the sign of the horizontal asymptote. This will work for you as long as the horizontal asymptote isn't 0, because 0 is neither positive nor negative. If the horizontal asymptote is 0, then you have to use something else to get one of these. You can test a point, or you can use the y-intercept or something like that. But now that we've got this guy and all of these, we can go ahead and fill out the rest of our sign table here. We're going to become positive because that's odd multiplicity. We're going to switch again because that's odd multiplicity. We're going to switch again because that's odd multiplicity. We're going to switch again because that's odd multiplicity. So I want to know, where is this function greater than or equal to 0? All right, this was my step 4. So where is my function greater than or equal to 0? Well, that means I'm asking where is this apparatus positive? So that's this region and this region. From -2 to -1, unioned with 2 to 3. And this time we need to be careful with the endpoints. So let me start with -2. Should I use a bracket or a parentheses on this, and why?
Is it a bracket?
It is. Yep, it is a bracket. So why should I be putting a bracket here?
Is it because the inequality is greater than or equal to?
True, right? The greater than or equal to means maybe we have some brackets. If it was a strictly greater than, then it would all be parentheses. But there's one other subtlety here. If you plug -2 into this function, what do you get?
0.
The audio cut out there. I couldn't quite hear. What do we get when we plug -2 in here?
0?
The y-intercept? No.
No, not the y-intercept. The y-intercept is always coming from x equals 0. If you plug -2 in here, then this piece is -4, this piece is 0, this piece is -5, and this piece is -1. So you'd have -4 times 0 over -5 times -1. That's 0 over 5. And 0 over 5 is 0. So we can include the -2 because when you plug -2 in here, you get 0. And 0 is greater than or equal to 0. So in other words, you just test the endpoints individually. You plug them into this function. You don't need to write it out. Usually you'll be able to see it right away. You don't actually need to write it out. But if it helps you to write it out, you can. What about the -1? What happens if I plug -1 in here?
Wouldn't the bottom be 0?
Good. If we plug -1 in, the downstairs here is going to be 0 because that -1 came from this factor. So should I use a bracket or a parentheses on the -1?
Parentheses?
Parentheses, good. This thing is not true when x is equal to -1. This thing is undefined when x is -1. So -1 cannot possibly be a part of my solution set.
So if it's undefined, it's parentheses.
Yes.
Okay.
All right. If I plug in 2, then the top is 0, and 0 is greater than or equal to 0. So that's good. We'll keep him. If I plug in 3, then the bottom is 0. The thing's undefined again. So this guy gets a parentheses. Not too bad, right? That's our answer. Okay. I'd like to do maybe 2 more. And this first guy, let's do here. I'll have done a bunch of the algebra steps for you. Okay. So let me change this to a greater than or equal to. Those are tougher. All right, so somebody has already done us the favor of pulling everything to one side, having a common denominator, factoring top and bottom. It's all been done for us. Yay! So steps 1, 2, 3 have already been done. That's nice. So we jump straight to step 4, where we write down those cut points, plug them on a number line. This factor is 0 when x is -2. This factor is 0 when x is -1. And this factor is 0 when x is +1. The reason I'm choosing this example is because it's actually one of the only examples in your textbook where you have a multiplicity other than 1. So the -2's multiplicity is 1. The -1's multiplicity is 1. And the +1's multiplicity is 2. Now, again, here I can use the horizontal asymptote to get the sign in the far left region. If I multiply this out, this is x squared minus 2x plus 1 over x squared plus 3x plus 2. So this has what horizontal asymptote?
Is it 1?
The degree of the top and bottom are the same. They're both degree 2. So we take the ratio of lead coefficients. That's 1 over 1, which is 1. So the HA is the line y equals 1. In particular, we're positive. Now, as we jump over this multiplicity 1 thing, we're going to change sign because that's an odd multiplicity. As I jump over this multiplicity 1 thing, we're going to change sign because that is an odd multiplicity. And as I jump over this thing, I'm not going to change sign because that is an even multiplicity. So what's my solution set look like? From -infinity up to -2, union with -1 to 1, union with 1 to infinity. And the same, bracket parentheses question needs to be answered here as in the other one. The answer we base it off the top of the.
Would -2 be parentheses?
Good. So the -2 is coming from this factor downstairs, which means he gets a parentheses, not a bracket. If we plug -2 into this apparatus, the bottom will be 0, so I cannot include him. What about the -1?
Would that be a parentheses as well because -1 would make it 0 on the bottom?
Good. So this factor downstairs is the factor that gave me the -1. And if I plug -1 into this thing, the bottom will be 0, so I cannot include -1. What about the +1?
Would that
We
be a
give it a bracket.
bracket?
Yeah, this would be a bracket. And here again, a bracket. Nifty, right? Now, a fun fact, you may not notice this, and I wouldn't take off points if you didn't. You can rewrite this as -infinity to -2 union with -1 to infinity. Because from -1 up to and including 1, together with 1 including 1 up to infinity, these guys stack right on top of each other. But either form would be acceptable. I would take this. This is maybe a little nicer. If this was a strictly greater than, then these would all be parentheses, and you wouldn't be able to combine the two last ones.
For the last one where you said that -1 goes to infinity, and how you can skip the step above it, is that because there's brackets because one's included on both of them?
Yeah. Yep. Yeah. If you were to graph this first set on the number line, here's -2, 1, and 1. The interval from negative infinity up to -2 with the parentheses there is like this, right? Everything up to but not including -2. The interval from -1 to 1 with the paren on the left and the bracket on the right is like this. And then the interval from 1 to infinity with the bracket on the left is like this. So the 1 is included in both of these, right? So this interval here is actually the same thing as -1 to infinity like this.
Okay, and if it was not included, you wouldn't be able to do that.
Correct, yeah. If these were both parentheses right here, then 1 is not a part of this guy, not a part of this guy. So when you union them, 1 still wouldn't be a part.
Okay, thank you.
Yeah, of course. Okay. I've got one more problem that I plan to solve with you guys today, and we're moving on at a pretty good clip here, so we might have time for even one more after that. But the last one that I wanted to work here involves a fair amount of algebra. So let's have a crack at this. All right. So here we got to do everything. I'm going to begin by pulling all the stuff to one side. And since there's 2 terms on the left, 1 term on the right, I'll pull this guy over. So that'll give me 1 over x plus 1 over x plus 1 minus 2 over x plus 2 is less than 0. Then I need a common denominator. What am I going to use for my common denominator here?
Would it be x times x plus 1 times x plus 2?
Very good. So this guy is going to need x plus 1 times x plus 2. And he will become x plus 1 times x plus 2 over x times x plus 1 times x plus 2. Then the middle term, he needs the x and the x plus 2. So he will be x times x plus 2 over x times x plus 1 times x plus 2. And the last guy, he has the x plus 2, so he needs the x and the x plus 1. So he'll be 2x times x plus 1 over x times x plus 1 times x plus 2. And all of this is still less than 0. Now, putting these together into one fraction, I get x plus 1 times x plus 2 plus x times x plus 2 minus 2x times x plus 1 all over x times x plus 1 times x plus 2 all less than 0. The bottom is factored, but the top I need to factor. And the only way to factor such a thing is to multiply everything out, combine your like terms, then factor. So we got to do it. If I FOIL this out, I'll get x squared plus 3x plus 2. If I distribute this, I'll get x squared plus 2x. And if I distribute the minus 2x over this, I'll get minus 2x squared minus 2x. So what do we have here? What are my x squareds? I've got 1x squared here, plus 1x squared here, minus 2x squared here. That's 0x squared. I've got plus 3x here, plus 2x here, minus 2x here. That's 3x. And the constant term, I just have a plus 2. And this is less than 0. So the numerator turns out to be linear, which means there really isn't any factoring work to do here. I could force factor out a 3. It's an option, but it's not really necessary. We just want to try and read off our cut points. What you got for me? What are my cut points? Well, 0 from this guy, -1 from this guy, -2 from this guy. And what about from the top? Where is that top 0?
-2/3.
Yeah, if you set 3x plus 2 equal to 0, you get x equals -2/3. And they're all multiplicity 1 again. So I'll put -2 over here, -2/3 here. Oops, sorry, -1 would be next. I'm sorry. Then -2/3. And then 0. So the one thing about this, you really do need to make sure you put these in the correct order on the number line. So -2 is the most negative, then -1, then -2/3, then 0. Okay. Here, my horizontal asymptote is the line y equals 0. The bottom is degree 3. The top is degree 1. So the horizontal asymptote will not save me. So to get started filling out our signs, I need something other than the horizontal asymptote. Another thing that I often like to use is the y-intercept, but unfortunately, this factor makes the whole thing undefined when x is 0. So I can't find, this doesn't have a y-intercept either. So what do? We got to test a point. This is the only situation where you need to do any test points. And I would probably come over here and say, let's test x equals 1, because that's easy enough. If I plug 1 in for x here, I get 3 plus 2, which is 5, over 1 times 2 times 3 is 6, which is positive. So we are positive in this region. And now all the multiplicities were 1. So we're going to change sign as we hop over each of these. So at most, test 1 point. Never need to test more than 1 point. Alrighty, this is a strict inequality. This is not a less than or equal to, it's just a straight up less than. So I don't need to worry about brackets or parentheses. I'm just looking for places where this thing is strictly negative. So that's here to here, and here to here. So the solution set is the open interval from -2 to -1, unioned with the open interval from -2/3 to 0. Any questions on this one?
For the horizontal asymptote, you go y is equal to 0 because the lead coefficient of the top is smaller than the one at the bottom.
Not lead coefficient, but the degree.
The degree, sorry.
Yeah, so the degree of the top is 1. And if you multiplied out this bottom, you'd see that the largest power of x here is 3. So the degree of the bottom is 3, which is bigger than the degree of the top, which is 1. So yeah, the HA is y equals 0.
Thank you.
So yeah, and then there was a question I got in the chat there. So I'm choosing to test x equals 1. I had to, because I can't get any of these signs from the horizontal asymptote or from the y-intercept, which are kind of the two easiest things to find. I had to test some point. And the easiest one for me to test is 1. Right? It's just if I had to pick a number to plug into this, what number do I want to plug in? Well, 0 is normally nice, but I can't plug in 0. The next nicest thing for my lazy ass to plug in is 1. So I figure, okay, I'll test x equals 1, which is an x value in this region. And when I plugged x equals 1 into this thing, I got 5/6, which is positive. So I put a plus here, and then everything else came from the multiplicities.
In the same sense, you could test x equals -3, right?
Yep. Yeah, we could have tested -3, but I'm too lazy. I'm so lazy. Even the idea of plugging -3 into this is more work than I want to do, right? We've already done so much work. But yes,
Right, but by the
yep, we definitely could do that instead if we wanted. All right.
Actually, sorry, that might be a dumb question, but why aren't you including infinity in this one? Is it because both ends are positives?
Well, so the inequality is asking me where is this function less than 0? So I'm trying to figure out, instead of looking for where this function is positive, I'm looking for where this function is negative. So the function is positive at both of these ends here. So it like 0 to infinity, that's not a part of my solution set because the function is positive there. And -infinity to -2 is not a part of my solution set because the function is positive there. So the only solutions to this inequality are the intervals where this function is negative, and that's here and here.
Thank you.
Yeah, less than 0 means negative, greater than 0 means positive.
Could you remind me just when or why exactly the signs change?
Yeah, so the rule is as we hop over an odd multiplicity cut point, the sign will change. And as we hop over an even multiplicity cut point, the sign won't change. So it's based on the multiplicities of each of these cut points. If it's an odd multiplicity cut point, we will change sign. If it's an even multiplicity cut point, we won't change sign.
Okay, thank you.
Yeah, of course. Maybe one last word on this before we go. So Most of the problems you're going to encounter from this section are just like, here's an inequality, solve it. But remember, inequalities can show up when you're looking for domains also. So another example of a problem like this would be find the domain of the function f of x equals the square root of x to the 4 minus 1. So recall, if you have an even root with some variable stuff underneath, that's one of our domain red flags. So here, the red flag is variables under the square root. And so we need the inside to be greater than or equal to 0. In other words, we need to solve the inequality x to the 4 minus 1 is greater than or equal to 0. And this can also be factored as a difference of squares. This is x squared minus 1 times x squared plus 1 is greater than or equal to 0. Again, using that a squared minus b squared thing. And then x squared minus 1 can be further factored as x minus 1 times x plus 1, again, as a difference of squares. X squared plus 1 does not factor. He's irreducible. So I'm not going to worry about the x squared plus 1. So my cut points here are positive 1 and negative 1. I don't get any cut points from x squared plus 1 because his roots are not real. And here we could get away with using the polynomial end behavior. So here my degree is even and my lead coefficient is positive. So my end behavior is as x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to positive infinity. So we're going up on the outsides. And then both of these are multiplicity 1. So as I hop over here, I would become negative. And as I hop over here, I would become positive. So the domain here is the solution to the inequality x to the 4 minus 1 is greater than or equal to 0, which is negative infinity to negative 1 union with 1 to infinity, always parens on the infinities. And when you plug in negative 1, you get 0 is greater than or equal to 0, so this would be included. And the same thing, when you plug in 1, you get 0 is greater than or equal to 0. So here would be my answer. I just wanted to show you one example where the problem has like a little bit of abstraction, where you're not just told solve this inequality, you have to figure out the relevant inequality. You're not going to be asked for a range for a function like this. The only case where I would ask you for a range is where you know exactly what the graph looks like, and then you would get the range from the graph. Okay. This is it. This is it. We are now done with this section. Is there anything you guys would like to ask in the 4 minutes we have remaining?
Why, excuse me, why did you, why is there only 3 point and not 4? Because the x squared minus 1, you turned it into x squared minus 1 times x plus 1. and then you kept the x squared plus 1 as it is, if you know what I'm saying, sorry.
Yeah, I do. So this guy doesn't have any real roots, right? He's irreducible. The roots from this piece are I and negative I, and neither of those are real numbers. So remember at the very start when I showed you this, I said it's not something you're going to run into, but the cut points are always the real numbers where any of those factors are 0. So the only real roots for x to the 4 minus 1 are positive 1 and negative 1. So in other words, this guy doesn't factor. This guy can't give me any cut points because his roots are non-real complex numbers. I can't plot I on a number line.
Okay, thank you.
Yeah, no problem. No problem. It is an interesting question, and asking what's the domain of this thing in the complex numbers might be a question worth investigating. It turns out the domain, if you're willing to work with complex numbers, the domain would be the whole complex plane. But questions like that are well beyond the scope of this course. So when it comes to finding domains or solving inequalities, we're only ever working with real numbers. Yeah, there's a mention about the Discord link expiring. I'm sorry about that. Those expire every week, and I just honestly, I forget to refresh them. So let me go ahead. I'll paste a fresh link in the chat here. Is there anything else you guys would like to ask? Remember, this is our last meeting before the test. Test 2 is on Tuesday of next week.
For those of us who want to take it at the testing center, do we still have to tell you this time around as well?
Nope, I'm going to make a general reservation for the whole class. So anybody who wants to show up there can show up there. Just be aware that they may ask you to wait a little bit.
And that doesn't, because I know last time they wouldn't let us in until 11. So that doesn't
That's
hurt.
true. I'm sorry. So I should have been more clear. I said this at the start of class, but yeah. So the test isn't going to open until 11. Can't take it early, but you can take it from 11 to any time in the rest of the day.
But if we get there at like 10:45 and they don't let us in until like 11:10 and we sit down, that doesn't hurt the actual time that we have when we start it.
Correct. The timer will start once you get into the test, not before.
Okay. All right, thank you.
Yeah, of course. I'll go ahead and paste that Discord link into an announcement here too. Anything else you guys would like to ask?
Hello, Professor. Could I just talk to you after class?
Sure. So here's the new link. Alrighty then, I'm going to go ahead and wrap things up here. Was that Whitney or who was that? Sorry. Whitney, right? Yeah.
That was me, Whitney.
All right, cool. Yep, the rest of you guys are free to go. Whitney, I'll go ahead and create a breakout room because we got to do this kind of quickly because I do have another class. So you'll get an invite to a breakout room here. Y'all are welcome to go. And then Whitney, I'll ask you to just join that breakout room. I'll follow you in there. We can talk.
Okay.
Really quick, this
All right, what's shaking?
Hello.
Hey.
Yeah, I just wanted to talk to you because I've just been like catching up with all my courses, and I just wanted to like ask like if there was any chance of from now on improving my grade in this course.
Yeah, there's always room for that. In this class, we do replace the lowest midterm by the final, so it's possible to get a 0 on the first midterm and still get 100% in the class. But certainly there is room to improve. How did the first test go for you?
I'm gonna be honest, I didn't study for the first test, so I didn't do that great. But I've been like actively trying to study for the second one so that I do better.
Good. Yeah, we definitely need to study. I know that like sometimes in high school or earlier classes, it's possible to kind of just get away without studying, but that certainly isn't true here. So definitely prepare as much as you can. The best way to prepare is by solving lots of problems. So make sure you're solving all the homework problems and quiz problems. Don't use things like Symbolab or Mathway. If you need more time on those, I'm happy to extend them. It's much better to take more time and solve them yourself than to use something else. I did just really quickly here pull up your written work from the first test. And my other piece of advice would be show me everything. So we only had written work for a few problems there. And it looks like maybe you were trying to do a lot in your head. Take the time and write out all your steps, because the more you write out, the more partial credit I can find. If something is blank or there's very, very little work, then it's hard for me to find partial credit to give. And I want to give partial credit. So definitely on this next test, write out all the steps for the free response problems, show every little bit of work that you can, and that way I can get in there and try to find partial credit for you.
Okay, and then you said the midterm grade, like you dropped, or is it the lowest test grade gets dropped by the final?
Yeah, the lowest test grade will get replaced by the final. So if your lowest test grade is like a 50 and then you get a 70 on the final, in addition to having that final be your grade 70, I will go back and replace that lowest midterm, that 50, by a 70 as well.
Okay. Yeah, I didn't really have any, I'm just trying to, because I've pretty much caught up in my other classes. I'm the type of person where like I have to study for one and like get one caught up and then do the other. So then now I'm trying to work on doing better in pre-calculus.
I see. Okay. Yeah, everybody has a different strategy that works. Generally, I wouldn't advise like ignoring one class while working on the others, but I understand if you found a system that works for you, that's fine with me, of course. Just make sure that you put in as much time as you can between now and Tuesday. That way this next test is better and you're on a path where things are feeling better. I think once you get into that place where you're a little bit more confident, everything just flows so much easier.
Okay, and you said the test is on Tuesday. Can I, if I elect to take it online, then that's fine. Like I just have to do it the same way we did it last time.
Exactly. Yep.
Okay. I don't think I have any more questions.
All righty then. I will I'll see you on Tuesday.
I'll see you on Tuesday. Thank you.
Of course, take care.